Hello and welcome to NPTEL online certification course on aero engine gas turbine cycles. This is lecture 14. In last lecture we were discussing about the single spool turbojet engine analysis for the ground condition. Then we were discussing the effect of various cycle parameters on the performance of the engine. And if you recall what parameters we are discussing, they are named as a pressure ratio and turbine entry temperature or turbine inlet temperature. So, we have discussed the effect of these parameters on various performance parameters like thrust, thrust specific fuel consumption and efficiency. So, we have discussed with effect of pressure ratio maintaining the turbine entry temperature to be constant. In second case, we have changed the turbine entry temperature and kept the pressure ratio to be constant, and then we were discussing about the effect of air mass flow rate. In last lecture, we were discussing about this numerical. So, the numerical what we have solved for the ground condition, now the company is planning to check their analysis for the cruise condition. And this cruise condition, it is at the flight altitude of 7000 meter with velocity say 500 kilometers per hour, temperature is 242.7 Kelvin and pressure at that altitude is 41.06 kilopascal. Now, pressure ratio, that is what is kept same, turbine entry temperature also is 1200 K. Air mass flow rate is 15 kg per second. The efficiencies here, they are say diffuser efficiency to be 100%, compressor efficiency 85%, combustion chamber efficiency 98%, turbine efficiency 89%, nozzle efficiency 94%. And it says like turbine shaft mechanical efficiency is 85%. It says like total pressure loss in combustion chamber is 3% of the delivery pressure, and total pressure loss in the tailpipe is 2% of delivery pressure. Here we need to take say Cp for air as 1005 joule per kg Kelvin, gamma equal to 1.4. For hot gas, Cp value is 1156 joule per kg Kelvin and gamma value is given 1.3. Consider say fuel heating value is 43,100 kilojoule per kg. Here we need to help them in order to calculate the nozzle area, nozzle radius, nozzle exit velocity, net thrust and thrust specific fuel consumption. So, we can understand now the scenario, that is what is little different here, as we are considering we are moving towards the cruise condition. So, let us see how do we solve this numerical. So, what all logic we know. Suppose if I consider this as a cycle, so very first component we have is our intake or say diffuser, and for that diffuser we are given with say Mach number, we are given with say temperature, pressure and diffuser efficiency. That is what will be giving me the idea for the calculation of what will be the total pressure and total temperature at the exit of the diffuser. The next component what we have is a compressor. For this compressor, we know what is the value of efficiency and what is the pressure ratio. Based on previous temperature and pressure, we can calculate what will be the temperature and pressure at the exit of my compressor. The component that process represent is 3 to 4, it is my combustion chamber, and for this combustion chamber we are given with the burner efficiency, we are given with the total pressure loss, turbine entry temperature, the calorific value of the fuel is given, and this is what will be helping us in order to calculate say my pressure at the entry of the turbine and the fuel air ratio. These parameters, they are very much important for the further processing. The component we have next is say turbine. For turbine, we are given with the mechanical efficiency, turbine entry temperature, and we have calculated the pressure and fuel air ratio from the previous component. That is what will be helping us in order to calculate what will be the temperature and pressure at the exit of the turbine. The next component what we have is a tailpipe. This tailpipe we are given with say total pressure loss, and that is what will be helping us for the calculation of total pressure and total temperature at the entry of our nozzle. And 6 to 9, that process which is representing my nozzle, for that we are given with a nozzle efficiency, and we can calculate what will be the critical pressure. We will be comparing that critical pressure with the atmospheric pressure, and that is how we will be calculating what will be my static pressure, static temperature and velocity at the exit of the nozzle. Now, once we are calculating all these cycle parameters, our next target, that is what is to calculate the performance parameter. So, very first performance parameter, that is what we will be calculating is in terms of thrust. We will be calculating thrust specific fuel consumption, we will be calculating what will be our thermal efficiency, what will be our propulsive efficiency and what will be our say overall efficiency. So, let us begin with the first component. Now, here in this case, this is representing the gas turbine engine line diagram, and here this is what is representing my TS diagram. Now, for this TS diagram, we need to remember very first component given to us, it is the intake. Now, for this intake, the flying Mach number, that is what is given. So, if you recall in previous numerical, when we have solved for the ground condition, my m infinity, that is what was 0. Here in this case, since my velocity is given 500 kilometers per hour, we can calculate what will be our entry Mach number. So, if I will be putting that number, I know what is my temperature, what is my velocity, and based on that we can calculate the entry Mach number. This entry Mach number is coming 0.445. Now, we know our diffuser efficiency. It says diffuser efficiency is given as say 100%. We have the correlation for the pressure. If you go through the fundamentals what we have discussed in second week, that is what will be helping you here. Here in this case, since we are having this m infinity component, that is the reason we will be having our exit total pressure term that will be coming into the picture. In previous numerical, if you look at my m infinity, that is what was coming to be 0, and that is the reason my pressure at the entry of my compressor and atmospheric pressure, that is what was saying. Here this is not the case. So, if we will be putting this number, my gamma is given 1.4, my entry pressure is given, Mach number is given, we can calculate what will be the exit pressure. So, inlet exit pressure, it is coming 47.04 kilopascal. Just be careful, these numbers what we are discussing, this is what is at the flying condition and it is at altitude, and that is the reason why these numbers are coming lower compared to our previous example. Now, next what we have is a exit pressure from the intake, and we know this is given by the isentropic relation, and if we consider my T infinity is given 242.7, Mach number is 0.445. So, if we calculate, it says exit pressure, inlet exit pressure, it is coming 252.31 Kelvin. So, I am sure you are able to calculate what will be the exit pressure and exit temperature from the intake. Now, this will be the input for my next component, what we say as a compressor. Now, for compressor, let us move ahead. We are given with the compression pressure ratio of say 3, we are given with say our compressor efficiency to be 85%. Can I repeat here?
Yes,
yeah. So, maybe from here. एक मिनट, ये है 49. नहीं नहीं, वो नेक्स्ट वाला ही रिपीट करूँगा. ओके, यहाँ ओके 50 में रिपीट करेंगे. ओके, now here in this case we are having the compression ratio. It is given, it says my pressure ratio for the compressor. हाँ, ये लास्ट था. अभी मैं नेक्स्ट जा रहा हूँ. ओके, the next component what we have is our compressor. So let's look at this compression process, that is represented by ideal process and actual process. Here we are given the compressor pressure ratio. My compressor pressure ratio is 3. So we can calculate our exit pressure from the compressor, and this is given by 141.12 kilopascal. Now in order to calculate my temperature, we can use this correlation what we have derived earlier, in which it is correlated with my pressure ratio and compressor efficiency. So if I will be putting this number, my T02 from previous calculation, it is 252.31, my pressure ratio is 3 and compressor efficiency is given 85%. So this will be giving compressor exit pressure to be 361.76 Kelvin. Now the next component what we have is our combustion chamber. So for combustion chamber, the information given to us, it says like ideally we are assuming our combustion process or heat addition process to be happen at constant pressure, but there are some losses we have discussed in our second wind class. So we can say the drop of pressure, it is given 3%. So if we calculate this as a case, my exit pressure from the combustion chamber, that is what is coming as say 136.89 kilopascal. Now this is what is representing my combustion chamber, and if I will be doing this as a control volume, I say my mass flow rate entering to the combustion chamber, that is what is say m air or m infinity. This is the amount of fuel what we are adding, and this will be the exit, that is nothing but the summation of m infinity plus mf. So it says this is what is my mass balance. Now here in this case, if I will be putting my energy balance, then I will say my entry to the combustion chamber, that is given by m infinity into H03. The amount of heat what we are adding is mf into calorific value, but the burner efficiency is given. So it is given by burner efficiency into mf into qr, and at the exit of my combustion chamber, I will be having the total mass flow rate to be approximately m infinity plus mf into H04. This H04, it is nothing but that is what is the raise of temperature. So if I will be writing this in terms of my energy balance and simplifying this, it says my fuel air ratio, that is what is given by this correlation. Now be careful here, this T04 is my turbine entry temperature. I need to take my Cp value for hot gas. Same way T03, that is what is my exit temperature from the compressor, and that we are taking Cp of cold air, and this is what is a formulation. So let us put the number. It says my Cp value for the hot gas is 1156, my turbine entry temperature it is given 1200, Cp value for air is 1005, So, if we will be putting all this, then it says my fuel air ratio is coming 0.025. Be careful what calorific value is given, that is in terms of kilojoule per kg. So, either we will be taking all parameters in kilojoule per kg or convert that into joule per kg, otherwise there are chances that your fuel air ratio will not come in the range. Okay. Now, the next component what we have, we can say this is my turbine, and for turbine, for the actual condition, that is represented by process 4 to 5. We know for this turbine, that turbine it is mainly being used to rotate the compressor for aero engines, and that is the reason why my energy balance, I say work done or work required for the compressor, that is what is equal to work developed by the turbine, and we are incorporating our mechanical efficiency. So, my work done or work required for the compressor, that is given by mCp delta T0, that is nothing but T03 minus T02. Same way for the turbine, here we need to be careful, my mass flow rate it is given by m infinity into 1 plus f Cp T04 minus T05. My turbine entry temperature will be larger, and based on that we can calculate what will be the turbine exit temperature. Now, if we will be putting all this number, it says my turbine exit temperature is coming 1090.7 Kelvin. Okay. Now, this is my temperature. I am also interested in what will be my pressure. So, in order to calculate the pressure, we have our fundamental correlation. It says my turbine efficiency, it can be correlated by actual work divided by my isentropic work, and if we will be simplifying this, it will be written in terms of my pressure ratio, or we can say for turbine it is expansion ratio, it is P04 by P05. Here this is what is taken as a reciprocal, because we are interested in calculating P05. So, this we can calculate by putting T04, T05 and my turbine efficiency. So, if we will be putting all this number, it says my exit pressure from the turbine, that is what is coming as 85.77 kilopascal. Okay. Now, the next component what we have is our tailpipe. Now, tailpipe, that is what is a connecting device between the turbine and the nozzle, and we can say it is a pipe of constant area, and for that it is given like we will be having the drop of pressure, it says 2% pressure that will be dropped in the tailpipe. The process we can consider as a adiabatic process, and so we will be putting here this P06. If we calculate, it says my P06 it is coming as 84.58058 kilopascal. My temperature, that is what will be remains constant, because I say it is a adiabatic process. So, my T06 and T05, that is what will be same. So, it says my tailpipe exit temperature is 1090.79 Kelvin. Now, we can say the next component what we have is our nozzle, and this nozzle we can say the flow will get expansion. So, this expansion process we have specifically mentioned. There is a special method here for nozzle. The calculation need to be done in terms of critical pressure ratio. So, this is representing the critical pressure ratio correlation, and here in this case if we consider, it is a function of nozzle efficiency. So, let us put the number, and if we will try to calculate, it says my critical pressure ratio it is coming as 44 kilopascal. So, my critical pressure is 44 kilopascal. Now, we will be comparing this critical pressure with our atmospheric pressure, and if we look at the atmospheric pressure, it is given as 41.06 kilopascal at particular altitude. That means my critical pressure is greater than that of my say atmospheric pressure. So, under that condition we can say our nozzle is a choke nozzle. So, if you recall in previous numerical, it was reverse case, it says my nozzle was unchoked, but you can understand the same engine when it is flying at the altitude, that is what will be having choking condition. So, under that condition my exit pressure will be critical pressure. So, I will be taking P9 equal to Pc, that is what is equal to 44 kilopascal. Now, let us try to calculate the parameters here. We are interested in calculation of what will be my exit velocity. Now, in order to calculate that exit velocity, we are looking for say exit static temperature. So, this temperature we can calculate by using this correlation. If we will be putting this number, it says my T9, that is nozzle exit static pressure, it is coming 948.51 Kelvin. Since this nozzle is choke nozzle, we can calculate our exit velocity. It is given by root gamma r t, and here t is T9. So, if we will be putting this number, gamma equal to 1.3, r equal to 287, and my T9 as say 948.51, my nozzle exit velocity is coming 594.89 meter per second. Now, based on all these cycle parameters, our next target it is to calculate the performance parameter of the engine. Now, in order to calculate this performance parameter, very first parameter we have is our thrust. So, here in this equation, if we look at my m infinity, that is known to me. This F is fuel air ratio, that is what we have calculated. V9 we have calculated, V infinity, that is what is given to me, and here in this case this is what is my pressure value. Now, I am having a known parameter, that is what is my area A9. So, in order to calculate this area, we will be using our fundamental equation of continuity. It says my m dot, it is given by density into area into velocity at the exit. Now, here in this case the parameter rho 9, that is exit density, that is unknown to us, that can be calculated by P upon RT, and we know what is my P9, we know what is T9. Based on that we can calculate our density. This density is coming as 0.162 kg per meter cube. Once this is known to us, we can calculate our area, nozzle exit area, and it is coming 0.16 meter square. Now, we are interested in what will be the radius at the exit, that can be calculated by pi r square, and if we put this number, it says my radius is coming 0.226 meter. Now, once these parameters are known to us, we will be putting these numbers. Be careful here in this case, when we are having our nozzle to be choke condition, that is what will be giving us the benefit of additional thrust, and this additional thrust is because of P9 minus P infinity into A9. So, if we will be putting this as a number, here in this case my thrust will be coming as 7481.4 Newton, or we can say it is approximately 7.5 kilonewton. Now, we will be calculating our next parameter, that is thrust specific fuel consumption. In order to calculate the thrust specific fuel consumption, we must know what is the fuel mass flow rate, that is calculated based on fuel air ratio, and this is coming as 0.375 kg per second. Now, let us put this number here in terms of thrust specific fuel consumption, and this is coming as 0.051 gram per Newton second. be careful about the units here. The next parameter what we have is in terms of the propulsive efficiency. Here in this case, since my V infinity is known, so propulsive efficiency calculation will be coming into the picture. Just recall when we have solved the previous numerical at the ground condition where my V infinity was 0, that is why my propulsive efficiency was coming to be 0. Here in this case my V infinity is known. So, let us put this number. If we are putting this number in terms of V9 and V infinity, we will be calculating our propulsive efficiency, and this is coming as 0.394. Now, we will be calculating our next parameter, that is thermal efficiency. This thermal efficiency we can say by this. Okay. Here we are putting these numbers in terms of output by input, and input value, that is what is my MF into CV. We will be calculating our efficiency, this is coming as 16.32%, and overall efficiency is given by thermal efficiency into propulsive efficiency, and this number is coming 6.43%. So, we can say now here in this case we are having propulsive efficiency and overall efficiency also coming into the picture. So, be careful when we are doing our calculation at the ground condition, when we are doing our calculation for the cruise condition, this parameters calculation, it is very important. Okay. Now, let us try to put it in a summary point here. So, when we are flying at 500 kilometers per hour, at particular altitude where we are having temperature and pressure, that is what is known to us, and if we do the calculation, it says my net thrust is coming 7481.4 Newton. Same way our thrust specific fuel consumption is coming 0.0501, propulsive efficiency is coming 39.4%, thermal efficiency is 16.32%, and overall efficiency is say 6.43%. Now, here if you look at these two are very important plots in terms of say ground condition and when we are talking about the cruise condition. What is the difference? Just try to identify the difference. Let us see what is the difference. So, this difference it is coming here when we are having the diffuser. So, when we are flying at the flying condition, we will be having our inlet pressure to the compressor, that is what will be different. Okay. Now, this is what will be giving the overall idea about our calculation for. Let us try to understand how these parameters will be affecting our performance. So, my performance parameters we can say they are mainly thrust or specific thrust, thrust specific fuel consumption, fuel air ratio, propulsive efficiency, thermal efficiency, overall efficiency, and we know this is what all will be depending on what is my compression pressure ratio, turbine entry temperature, efficiency of the individual component, flight speed and flight altitude. So, this is what we have done for our ground condition also. Just realize here we are having the flight condition. So, we must discuss what will be the effect of variation of this parameter on the performance. So, let us take one by one. Say very first we will be taking our say pressure ratio. What will be the effect of pressure ratio when we are putting turbine entry temperature to be constant. So, here this is what is representing. It says with the increase of our pressure ratio, this is my design condition. If we are increasing our pressure ratio, my thrust will be increasing. The reason can clearly be seen here. What we can say, when we are increasing our pressure ratio, we will be having the rise of my say exit pressure from the nozzle, we will be having the rise of velocity, there will be change in my fuel air ratio, but the change is majorly with the change in pressure at the exit of the nozzle, and that is what will be responsible for the increase of the thrust. Same we can represent in terms of say specific thrust, where I am having my m infinity to be constant. Now, in the case we are interested in what will be my thrust specific fuel consumption. Here in this case we can say my thrust, that is what is coming in the denominator, and when we are increasing our pressure ratio, as we have discussed, my pressure is increasing, my thrust will be increasing, and that is what will lead to decrease the thrust specific fuel consumption. So, we can say this is what is one of the indicative, like if you would like to reduce the thrust specific fuel consumption, you need to rise with the pressure. Now, let us look at what is happening with my efficiency terms. Here in terms of efficiency, we can say this top one, that is what is representing my propulsive efficiency, thermal efficiency and overall efficiency. So, here in this case if we look at, it says in the flying condition, when we are increasing our pressure ratio, since my thrust, that is what is increasing, that means my propulsive efficiency will be increasing. Same way here if we look at, this is in terms of my say thermal efficiency, since my thrust is increasing, my fuel air ratio will be increasing, and that is what will lead to increase the thermal efficiency, and there is a rise of overall efficiency with the rise of say pressure ratio. Now, let us look at the next parameter, where we will be putting say effect of turbine entry temperature and putting the pressure ratio to be constant. So, here in this case if we look at, it says with the increase of turbine entry temperature, say this is my design condition, if we are increasing the turbine entry temperature, the thrust will be increasing. Same way my thrust specific, say specific thrust also will be increasing, and very important, we are discussing about the thrust specific fuel consumption. Here my trend will be different compared to the previous discussion. Here in this case my thrust is increasing, but at the same time we need to be careful and we need to realize one thing, in order to raise the turbine entry temperature, the amount of fuel required, that will be increasing, and that is the reason why my thrust specific fuel consumption, that will be increasing. Now, this is what is indicative of say my propulsive efficiency, thermal efficiency and overall efficiency. If we look at here, it says with the increase of my turbine entry temperature, we will be having say thermal efficiency, that is what will be going down, and that is what will be lead to give the overall efficiency to be lower. So, this is what is indicative of selection of turbine entry temperature, what need to be the turbine entry temperature for the specific say pressure ratio. Now, if we say what is the effect of air mass flow rate, we can say when we are increasing our air mass flow rate, my thrust will be increasing, because my area also, that is what is changing. In terms of say thrust specific fuel consumption, it has not major change. If we consider say efficiency term, will not be having the variation in terms of say propulsive efficiency, thermal efficiency, overall efficiency, but it says when we are increasing our mass flow rate, my entry mass flow rate, the nozzle area will be increasing. Okay. This is to handle the large mass flow rate. Now, in overall, if you will try to look at, this is what is a composite curve, what we were discussing in terms of my specific thrust, specific fuel consumption, and the parameter variation, we are having pressure ratio, turbine entry temperature. This is where we are having our design condition. Now, if we will try to realize this part, we can say in order to increase the specific thrust, we need to go with say higher pressure ratio, we need to go with say higher turbine entry temperature, but that is what will lead to increase my specific fuel consumption. And if you would like to move towards say lower value of specific fuel consumption, we need to compromise in terms of the specific thrust. This specific thrust, that is what is very much important parameter when we are talking for the application of aero engines. Now, this is what is a comparison part for say my ground condition and cruise condition. We will be realizing here my exit radius, that is what will be coming to be larger for the cruise condition. My thrust also will be say reducing in terms by around say 200 Newton. My thrust specific fuel consumption, that is what will be increasing, and my overall efficiency is coming in terms of 6.43%. Okay. So, under the cruise condition, it seems there is an improvement in terms of my thermal efficiency. That is what is indicative of the requirement. Now, this is what all we have discussed in terms of what is happening at the turbine say compressor entry. Now, let us try to compare this what all we have discussed in overall sense. Say we are having ground condition with us, we are having say flight condition with us. Let us discuss in terms of effect of pressure ratio, putting turbine entry temperature to be constant. So, this is indicative of flight condition and the ground condition. If we look at for the flight condition with the higher pressure ratio, we will be able to achieve the similar thrust as what we are achieving under ground condition. Same is the case. Now, here in this case, if we look at, it says my thrust specific fuel consumption, that is what will be coming to be higher in terms of my flight condition. This is what is because of what work we are looking for. This is because of the rise of my fuel consumption. Okay. So, here in this case, if we are comparing these two conditions under say ground condition and flight condition, this is what is my indicative, and this is what is representative in terms of my efficiency. If we look at for the ground condition, we are achieving higher thermal efficiency compared to our flight condition, and overall efficiency, that is what is having say rise with the rise of say pressure ratio. Now, the situation is what all we are discussing at this moment is giving the idea about the selection of what need to be my pressure ratio. Okay. At the same time, it is also giving the idea about what need to be my turbine entry temperature. So, let us look at say what is the effect of turbine entry temperature. Here in this case, if we are comparing, it says like there is not much variation with the rise of turbine entry temperature if we are putting say my pressure ratio to be constant in terms of thrust generation, but at the same time during the flight condition we will be having my thrust specific fuel consumption, that is what is going to be higher. Okay. So, here this is what is representing my thermal efficiency, overall efficiency and propulsive efficiency. So, all this together, that is what will be giving us idea about the selection of this parameter. Now, in next lecture we will be discussing about what need to be done, how do we decide this parameter, which parameter we are talking of is my pressure ratio, what need to be my turbine entry temperature, because that is what will be directly affecting on my performance parameter in terms of efficiency, thrust specific fuel consumption and the thrust generation. So, here we are stopping with, I prefer like you do your pen paper calculation, that is what will be building the confidence in terms of understanding this numerical. Okay. In next class we will be discussing some interesting case, that is what is of interest for all of us. Thank you very much for your kind attention.